Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Homework 6, where we put principal component analysis, logistic regression, and classification together in one assignment. So we'll come on down to this last assignment right here. All right. We are again using the San Juan River Razorback suckerfish as a data set. And I'm going to first read this introduction because there's a lot of details here that I don't want you to skip over. This is a long assignment. And that is, it looks very long, but it is not a long assignment for you. Okay, so most of the tasks that I ask you to do, you've done in previous assignments, so you'll be able to go and get pieces of code from those. Most of the challenging code I've written for you, and when I ask you to write code, I've usually given you an example to follow. So things should be fairly straightforward. Later code chunks depend on computations that I'd like you to do, and so I've commented out some of the later code chunks because they may not run until you've completed earlier chunks. So I do that by, after the triple tick, I press enter and I move the brace R brace inside the code chunk. Just bring that back up after the triple tick and that will then compute. All right, here's an overview of the assignment. Our goal is to develop a logistic regression model to predict the source of fish based on a principal component analysis components of the elemental isotopes and compare that logistic regression prediction model to the quadratic discrimination model. I've cleaned and transformed the data for you. I break the data into a training set and a test set so that we can use the training set to develop our model and then see how well they perform with the test set. That is, I take the data set and I just randomly partition it. I'll show you how I do that. We do a principal component analysis for each element. So BA, I think, has 2 elements. I combine that into a single one. Calcium just has 1, so it's the same as the principal component. I think both MG and SR have 3 or 4 components each. 3. By combining these isotopes into a single principal component, each can explain more. The first principal component can explain 99% of the variability of all 3 variables. This is really awesome. So we've done this. We'll do a great job doing dimension reduction. I do one of them. I do it for BA, and I just ask that you do the other 3 through copy and paste. Even though it's a bit tedious, I think that there's some value to you doing it yourself. You'll remember how to do it 2 or 3 years from now if you ever need to do this yourself. Logistic regression is next, and we do logistic regression on the training data. And I do an example using just the main effects, and that model doesn't fit well at all. What I recommend is putting in two-way interactions and quadratic terms. If you do that and then do backward selection, you will still end up with a model that fits the data well. So that is the strategy I recommend and that I expect everyone to do. The classification metrics on the training set are pretty good, and I ask you to define and interpret the sensitivity and specificity for classification using logistic regression. Next, we want to use the logistic regression model based on the principal components to do classification on the test set. And I do the hard part here of transforming the test set into the principal component space. This is I wouldn't expect any of you to really know how to do this. It's a tricky linear algebra transformation. But anyway, I've written the code so it works. The tough part is, right, so we've got this training set and we've calculated the principal components and we've developed this logistic regression model, and now we have to use this logistic regression model on the test set. Well, the test set isn't transformed via the principal components yet. So we need to get the test set into the same space, the same feature space as what was used in the training set for the logistic regression. So that's what this first bullet point is. I did that transformation. Then I've also have the code to do the classification using both logistic regression and the QDA. I'm only asking you to interpret the results of the classification, not to write the code to do it. Finally, consider how well the model worked and what could be done to improve the models. Okay, I'm not asking you to do any additional improvements. I just want you to brainstorm, right? Think about whether there's maybe other transformations to do, or put yourself in the shoes of the person who's studying these fish, and ask some questions about how you can improve the classification. All right, so now I'll run through it, and just to show you each part where you need to change things. But it is such a long assignment that what I would recommend is you pull this up in RStudio, and you're looking at the R Markdown file, and maybe step through this video as you're editing your own file. All right, so thanks again to Adam for providing this data. It's the same data as before. Razorback suckers from 2014 from the San Juan River. We've got these 4 elements. And one issue is that, well, we're going to sort of ignore that. We'll skip over that. The main thing is we want to distinguish between 2 fish populations. One of them from ponds, so the Nap group, and the second one, the San Juan River fish from the river. So between the 2 wild fish, which fish are from ponds and which ones are from the river? We have, we're just looking at just these 2, the wild ones. All right, and our goal is to classify the wild fish into their locations of either pond or fish. First, we'll use principal components to reduce the set of highly correlated isotopes of the same element to a single principal component, and then we'll use a binary response where pond is going to be the success and river will be failure in our definition for success and failure in the logistic regression. We'll fit the logistic regression, do model selection, and finally we'll do classification and see how well the logistic regression model performs relative to the quadratic discriminant analysis. All right, I do all the cleaning here. This is basically the same as before. We start by reading the file. We omit missing values. We keep just the variables we want. We filter based on the 2 populations that we want. I remove some unusual observations. And then we change source to character so that we can create a new source variable. I'm just basically renaming Nap and SJR to be pond and river, so it's easier to talk and think about. Then I refactor that variable so that pond is the baseline and river is the second level. And I log transform the barium isotopes. All right, we have 375 observations. Next, I'm going to draw a subsample for basically test the training in the test set. Okay, a couple things here. So I'm going to select indices from the rows. So we have 375 rows. Is that right? Yes, 375 rows. So I'm going to take the numbers, the integers, 1 through 375, and I'm going to sample from those integers. I'm going to sample 100 to be the values that we're going to predict. And this vector holds those indices. So observation number 4 is going to be in the test set, number 9 is in the test set, 10 is in the test set, and so on, and there's 100 of them here. So then what we do is we make the prediction set, that's the test set, by, from the data set, slicing. A slice is a way of subsetting the rows based on their indices. So we're going to pull those 100 values and put those into the prediction set, and then we're going to do the same thing for the test set. We're just going to overwrite the original data set. So we're going to remove those indices and update our data set. This is our training set. All right, so now our training set has 100 fewer, 275 for dimensions, and the prediction set, or the test set, has 100. All right, so now we've got the data sets that we need to move forward. All right, we've got a big plot here, and you know, go ahead and plot this just to take a look at those. Let's see. Do I already have it very briefly? No, I don't. Okay. So the main thing really to convince yourself is that we're about to do the principal component analysis. So are the variables, are the isotopes within each element, all the bariums, all the calciums, all the magnesiums, all the strontiums, are those really highly correlated? And yes, they are, is the short answer. All right, so now we're going to do principal component analysis for each set of variables. So here we are. We've got going to do the principal components, and here are the two barium variables that we're going to combine into a principal component. We're not going to do it on the correlation matrix, though you could. Let's just assume that we're going to do it on the covariance matrix, and so keep core equals false. That principal component object is going into PCA underscore BA, and if we want to summarize it, take a look at this. Okay, half of your minds are getting exploded right now because the first component explains 99.8% of the variability of those two variables. Okay, that's what happens when you have correlation that's like 0.99. All right. Finally, we are going to create a new variable in our data set called PC1 underscore BA. And we are taking from the PCA object, we're taking the scores. The PCA scores are the values of the observations on the PCA scale. Okay, so those are basically our new observations. We have to specify the column component 1, and we're changing that to numeric. The last part here is a minus sign, and this is not very important. Let's see. If loadings for component 1 are negative, then switch the signs of the scores so that positive values of the original BA variables will still indicate larger values. Okay, so when I go up here, do we see? Well, these loadings are positive. I'm not sure what's happening here. It's possible that between running PCA a couple times that this has changed. But the main point here is that one point is that it matters not at all whether we flip the sign or not. But recall that PCA defines a direction, and if you take the negative of that direction and go the other way, it doesn't really matter in terms of the PCA. What it may affect your interpretation. So if you're I don't have a plot to refer to, but we've got these two BA values. So as BA 137 increases, does the PCA value increase also? And that's sort of what we're wanting for an interpretation, a variable that is easy to interpret. So if these loading values, if these two were both negative, okay, let's start with the example that we have. If BA is positive, then as the component 1 increases, then each of these BA values are going to increase also. So that's a nice interpretation because these BA values are positively correlated, and we want our component to increase in the same direction as the original BA values. However, it can happen sometimes that these components are both negative, and in that case, you can add this minus sign to undo those negative loadings. Okay, so in this case what I would do is, because I see that these are positive, I would come down here and remove this minus sign and have it be positive. Now there's another way to do this, I guess. I could have inspected the sign of the loadings, and if they were negative, I could have put a minus sign here automatically by writing code to do that. But I did not this time. All right, so note that component 1 explains 99.8% of the variability. So I want you to calculate the remaining features using this code below. Okay, I've got 3 places for you, and the main thing to do is to just take this code right here, copy and paste it. Okay, copy and paste this code, and copy paste this code, and then you can simply do a find and replace of BA, and change that to CA, and change that to MG, and change that to SR. Now for CA, you can do it exactly, you can use all the same code even though there's only one variable. Your principal component will be the same as the original observation. That's cool. It's probably easiest just to copy all the code 3 times, and rather than treat CA differently just because it has one variable. Okay, finally, for each of these, also report the proportion of variation as I did here. So you probably want to also copy this text because this number is coded. All right, so just some copy and paste to do. Next, plot the scatterplot matrix of the new PCA variables, and what the heck? It is going to look like something like this. Okay, so notice that I am selecting just those PCA variables here. I can make this a little bit bigger. Okay, and then they appear down here, and there's a quick look at them. So yours should look like this. All right, moving out of the way. All right, next, logistic regression. In this section, we're going to use logistic regression to develop a model using the PCA features to calculate the probability that a given fish is from the pond versus a river. All right, so first we're going to fit logistic regression, and I told you before that the model that I fit initially stinks. Now, here I am creating an indicator variable called pond, which is either going to be true or false. So if source equals pond, then the pond variable is going to be true, otherwise it's false. So here is the code. You'll need to move this up to the previous line after the triple tick. I can't run this code yet because these variables aren't created. So after you create them, then you can run this code. But notice if it's just a standard logistic regression model with pond and 1 minus pond as a response, and those 4 terms as the model, when you look at this, the deviance chi-square for lack of fit, it sucks. We have a very small p-value, which indicates evidence that the model doesn't fit the data. Okay, and then this backward selection is not going to help either. So what I recommend here is to use a model that has two-way interactions and the squared terms. So I'm going to just quickly show that on the screen. Okay, there you go. You've all paused it, and you've noticed that around those main effects, I've wrapped it with parentheses and put a squared term. That gives the main effects and the two-way interactions, and then to that I'm adding each of the squared terms. The I creates a new calculated variable, and in this case I'm taking each of the values and squaring it, and I'm adding all those together. Alright, so once you've done that, then you've got a full model. you'll find that the deviance lack of fit looks great. Even after doing backward selection, it's going to look good. So you're going to be happy with this model. All right, so here's the model that we're happy with. All right, next we're going to assess the prediction ability of our model. Let's see, should I tell you something? Sure, what the heck. If we go back just a hair, this p-value, I'm expecting that p-value to be 0.226. All right, so now we'll assess the prediction ability and choose a classification threshold. Okay, so in logistic regression, we have a prediction probability of success, right? So for every observation or for every combination of X covariate terms, you get a probability of success. So for example, you might have a p-hat of equal to 0.3 for a certain set of PCA variable values. And so below, we're going to summarize all possible thresholds using a receiver operator characteristic curve. You can learn more about that here. And we also extract what the optimal threshold is, which jointly gives the best sensitivity and specificity. So you'll need to uncomment this code. And from the ROCR package, we get these predictions, and we calculate these performance metrics, true positive rate and false positive rate. Those are going to be our axes. And then we put some of the performance information into this data frame for an ROC curve. We calculate this distance, which determines the optimal threshold value, which I print out. And finally, I plot that ROC curve. Okay, and since unfortunately that's not something I can show you because on the assignment, but I can show it over here. Let me just have this pop in for a moment. All right, so here's sort of what that would look like. My optimal threshold here is 0.27, and that gives a certain specificity and sensitivity. When I create the ROC curve, it looks like this. It always starts at 0, 0, and it always ends at 1, 1 in terms of the true positive rate on the y-axis and false positive rate on the x-axis. The diagonal line is sort of the 50-50 point. So if your classifier was no better than flipping a coin, then it would follow that diagonal line. We want to get it as high up into this top left corner as we can. These lines sort of indicate where on that curve is sort of the closest point to this on the curve, the closest point on the curve closest to the top left corner. All right. And all right. So then we're going to use those values for the sensitivity and specificity interpretation below. And all right, good. All right, so in addition, I put in some predictions from our training data set. I basically add what class we have classified into, whether we classify into a pond or a river. And this is how it works. We use a prediction, and the type response means that we're predicting the probability. So for each value in our training set, no, sorry, this is all still, in our training set, we make a prediction which gives us a probability, and we make sure that that's a numeric probability. And if it's greater or equal to our threshold, then we're going to classify it as being in the pond. Okay, so the probability of success is for the pond. If it's greater than the threshold, it's the pond. If it's less than that, then it's the river. And finally, this classification variable, which takes these pond and river labels, I'm going to convert into a factor variable. So finally, we have a way to calculate our confusion matrix for classification. We've got the true sources, okay, which are either pond or river. We have the class variable that we just created as our data. Those are our predictions, and we're going to use this function to calculate how well we did. Okay, so we'll scroll down a little bit. Here's our confusion matrix. Our diagonal elements are the largest. That's good. That doesn't always happen. It looks like our references, so pond, so 21 of our 94 were misclassified as river. And for river ones, we're also not classifying that great. The overall accuracy is 71%. These sensitivity and specificity values may actually differ from the ones above. Let me just double check real quick. Sensitivity, they do, yeah. Okay, let's see. Let's interpret these sensitivity and specificity values in this table. Okay, and if you don't know what these values are, here's some links for you to read and understand about them, and then give an interpretation. I didn't mean to tap on that, but okay, yeah. This Wikipedia article is extremely detailed, but what I recommend is just looking up maybe these two values here, sensitivity and specificity. Okay. All right, let's go back to yours. All right, finally, classification. So in this section, we're going to compare the predictions using logistic regression to the quadratic discriminant analysis that we used a couple classes ago. So we need to take our test set, those 100 observations we held out at the beginning, project them into the principal component feature space, and then do the predictions. All right, so there's a bunch of code here. It will just work when you plug it in. But there's a function that takes the data set and the PCA objects and does some matrix multiplication to get it into the PCA space. Looks like I'm also doing some plus signs and minus signs to make sure that they're going in the right direction. And finally, the test data set should look very similar to the training data set because it's sampled there. So here I'm plotting the test set, the predictions, and this plot should be just like the one previously. If things are sort of flipped on an axis, then that suggests that maybe you need to add or remove a minus sign here. All right, so finally, that section is really just getting the data into the right space. Do make sure that the transformation worked by evaluating this plot. Okay, I think I get to say finally. Finally, we get to do logistic regression and compare that to the QDA. So here we've got the prediction data set, and we're going to predict values just like we did before and compare it to that optimal threshold to create labels, classification labels of pond or river. And then we compare that with our predictions with what the true values are and look at the values, the sensitivity, specificity, accuracy, classification values that we looked at just previously. Next, we also are going to use quadratic discriminant analysis to see how well we can make these predictions. So we do the QDA function on the original data set using the principal components, and then we make predictions using our quadratic discriminant analysis, the function that we trained. We're going to use that on the new test data set, those predictions. And then I tidy it up a little bit and do a confusion matrix for the QDA. And so we're going to look at these error rates, or maybe accuracy rates is really what we're looking at. So summarize the accuracy rates and note any differences you observe between these two methods. Okay? Which method do you prefer? Would you prefer, if this was your data, would you prefer to use the logistic regression as a classifier or the QDA method? And then if you'd like, you can change the set seed value at the top just to see how drawing a different sample would change your results. Okay, you've got all your code working. You can scroll most of the way to the top. Oh, I shouldn't have done that. Set seed. There it is. So you could change this to another integer, like 27, or my favorite one is 76543 because it's a prime number. And just see whether the classification results depend very strongly on the subset that you used for prediction. I suspect it will change a little bit, but not very much. At the very end, do go back to the number 3 so that everyone has the same results to compare. All right. I guess finally, comment on whether you're surprised by the prediction accuracy on the test subset, right? So did the classifier work much better, worse, or roughly as good as you expected? And do you have any ideas on how you could have improved the classifier or information for the classifier to distinguish between these two sources? Recall that these two sources are a nightmare. These are the two that basically lie right on top of each other. By looking at the plot, to my eye, there's like no way to separate these. So that we could get 70% accuracy is a bit impressive to me. Though I also know that classifiers can sometimes distinguish groups that are hard for humans to see how to distinguish them. So I expect it to definitely do better than 50-50, but definitely not higher than, say, 80%. So anyway, that's a few comments on that. And that is the assignment. I hope you don't think that this is too burdensome. I think the actual work for you to do is not too great, but there are a lot of parts, and unfortunately, because of the dependencies of the code, there's a lot of code chunks that are just sitting here waiting to be uncommented, and so they can run. So I hope that after you do the PCA, that's the real thing that's holding all the rest of the code back is the PCA. Once you do the PCA, I think you can uncomment all the rest of the code and start seeing all the results, and then it won't feel like there's so much missing. All right. Well, I hope you have a good time with this assignment. This is probably my favorite assignment in the course because it combines ideas from 3 different areas, and this is a practical strategy for approaching this problem. So this is something that I have done in real life. So enjoy it. Bye bye.